Look like a green.
Is this it? Oh,
Yep.
sure. Okay. So our panel is entitled How to Make Sure Your Microgrid Will Work. And the idea is that you can use hardware in the loop and model-based engineering in order to do that. So what I'd like to do is sort of pose the issue of how we do microgrid development today. And that is basically a disconnected sort of process. And what we're going to work on is coming up with something that's a little more integrated. So today, one group of people go off and they look at the opportunity at a particular location, market, and so forth. They do techno-economic analysis, try and figure out what's this microgrid or this project going to look like. Am I going to have some storage? Should I have some solar? Is it going to pay in this market? And that analysis gets done. And then whatever products those people produce sort of go away, and someone else builds a model and says, well, what does this system look like? How's it going to behave and perform? Somebody else goes and does analysis and says, well, how do I keep this thing safe? And so they're all talking about the system, but they're not really looking at the system. They just sort of have separate views. And if one of them sort of changes their answer, it doesn't change everybody else's answer. So it's really not a very tightly integrated process. And it can be prone to not only sort of inefficiency, but potentially error. So the emergent approach is to use model-based engineering. And this isn't entirely new. We've been doing this in aerospace for decades. And so before we launch spacecraft, before airplanes fly, there's actually model-based analysis that's done, there's simulations that are done. And so they've worked on these very critical systems using this model-based approach. But the idea is, if you look sort of at the bottom of this slide, there's this funny V-curve that's highlighted in red. So if you're systems engineer, that's familiar. And so it basically represents the life cycle of developing something, and you move along from conception on through implementation and maintenance. But there's this dip along the way where you go from thinking about the system to thinking about all the parts of the system, and then back up, to again talking about the whole system. And so model-based engineering allows you to do that, to have one coordinated, integrated database or model of the system, and it represents the different attributes that people might want to query with regard to and do whatever their job is. But it's all integrated. And so in this case, on the right side, you see basically a computer with some pieces of controller hardware built into them that represent that computer-based integration. So if you do this really well, and you have a high-fidelity model, and you have computing capabilities to run it in actually real time, you can do something like they do in space and aviation. You have a flight simulator. And so if you can do this hardware in the loop simulation where you connect real-world devices to the computer interchangeably, and the system doesn't really care whether it's the real device or the virtual device, then you can really experiment and try things out. And that not only can streamline your design process, but it's actually useful, for example, if you're thinking about this question of resilience. How do I achieve resilience? What's it worth? Well, imagine at least if you have this model-based system, and you can sort of run it in simulation and see how does this overall system perform under different contingencies. But that's a lot more informative than asking what happens if this circuit fails, what happens if fire in that circuit. Well, that doesn't tell me anything about how my operation performs. So these metrics here represent the results of a VDC study that was recently done to investigate this question about hardware and loop testing. Does it really pay off? And so you can see that as a risk reduction mechanism, it's something that has some prospective value. So that's sort of the context of this model-based engineering and hardware in the loop testing that we propose to talk about. What I'd like to do is introduce our panel members, each of whom is very accomplished in this field and has a particular take on this. And each individual will kind of introduce themselves, what they do, and answer to this question quickly. And then after we throw a panel sort of presentations, we're going to open it up for your conversation. We've got HG continuing to sort of spur the dialogue, and Matt Baker from Typhoon will be out there trying to motivate you to really think beyond, the points that have been made and explore this further. So with that, I'd like to start the conversation with Scott Barron, who's a system engineer at Raytheon.
Hey everybody, my name is Scott Barron. I'm a system engineer at Raytheon. I've been there about 10 years and I've done quite a bit of work with model-based design and a handful of different systems. I think the best example of how model-based engineering really helps in what I do day to day is by thinking back about 10 years ago. I was working on a small hybrid power system project, and it was a battery, a generator, a couple solar panels, and it was supposed to run remotely, work forever, and basically not need maintenance for like 6 months or something. So one day I got a call and they had a generator that stopped working, and so they needed me to kind of see what was going on. They flew me out to the desert in New Mexico, told me here's the system, sat me down, and I sat down on a box, looked around, but there was nothing around me except sand, and they wanted me to figure out what was going on here. So that's kind of worst case scenario. That's what you really don't want to happen. So over the years, there's been a big push to do this model-based engineering. And at Raytheon, we started looking into using auto code generation to model something in Simulink and then deploy those models to a controller, or do some sort of program loop simulation. And so as that capability has evolved over the years, we've developed more and more complicated microgrid systems at larger scale. Currently, we're working on a microgrid project at Otis Air National Guard base in Cape Cod, and we're using the Typhoon system, and we have a full integrated microgrid model of the electrical system. And we have a controller for the battery system. We have a generator controller. And as we develop our supervisory controls for this, instead of going out to Cape Cod, driving down to the base, standing out there in the middle of the field, I can sit at my desk in Los Angeles, and I can connect up to the microgrid system. I can run our control software against that, and induce faults, see how the system's going to respond. And so, summarizing, it reduces integration risk and reduces the time frame to diagnose and troubleshoot issues by a huge margin. We recently had our first integration 4-hour supervisory control out in Cape Cod. And instead of spending weeks out there, we were out there for 4 days total, and we demonstrated control capability for 2 of the major subsystems there. I can't imagine that occurring 10 years ago when we first started this type of process.
Great. Thanks, Scott. Next, I'd like to introduce Ryan Smith, who's the Chief Technology Officer for EPC Power. I should have stipulated the question is, what's the critical problem that model-based engineering solves for microgrid development?
Thank you. Yes, I'm the Chief Technology Officer for EPC Power. EPC Power is a power conversion technology company, actually located only about 20 minutes from here. We produce inverters and DC-DC converters in the power range of starting around 150 kilowatts up to several megawatts. Primarily focused on grid-connected applications as well as microgrid applications. So in response to the question, I'm glad we're talking about how you should test rather than if you should test. So we're talking about how you should test. The spectrum of options is really arbitrary software-based models or models that are developed in a pure software environment that are designed offline and are designed to match the behavior, the expected behavior of specific components. That would be the software end of the spectrum. The other end of the spectrum would be putting together an entire microgrid system and then trying to test different operating scenarios on completed hardware. Hardware in the loop is pretty much right in the middle of those 2 options. And it's primarily what we rely on in EPC Power. The advantage of sitting in between those 2 options is your development time, any development time that you put into developing control software that runs on a hardware-in-the-loop system is directly applicable to your end product, because that same software goes into the end product. So you don't have to duplicate development effort. You don't have to duplicate developing a software model and porting it to hardware. The other advantage is that you can integrate hardware from manufacturers that don't necessarily want to or have the capability of providing you a model of how their particular component operates, whether that's a Schneider relay or a generator controller or some other component, a PLC. So the advantage is that you can integrate hardware that comes off the shelf without necessarily relying on a component manufacturer to supply a model. The last thing is you can, the last advantage is that you can keep your model-based tool chain pretty lean, because you don't have to maintain a software simulation system that is supported by one supplier, one customer, but then maintain a different simulation platform for your own control scheme to use. Pretty much the entire team can use the hardware-in-the-loop simulation system to perform the testing they're trying to accomplish.
Great, thanks, man. So you can see this panel is not a bunch of sort of theoretical folks. We're talking practical down in dirt, what do we need to listen to? So appreciate that. Our next speaker is Andy Haun, who's the CTO for Microgrids at Schneider Electric. Been around the block.
Yes, as I just said, I'm the CTO for Microgrids, where I've been a 30-plus year veteran of Schneider Electric doing offer development system products. And I think the key for us at Schneider in the use of model-based systems engineering and our hardware in the loop has been always around finding all the problems that our customers are going to have on products where we don't have a specific input and output defined, but one input or several inputs with a wide variety of outputs in order to test all the different things that the product would have to do and or the system would have to do. Would be impractically long for us to be able to deploy a solution that's going to be reliable in your applications. So what we've done is we've used hardware in the loop, and this would be decades ago with some kind of dedicated hardware testing and validation platforms to more flexible platforms that we have today, where we can program and adjust these systems that really try to represent the problems that the end user would be seeing with their solution, so that we can confirm that our products and our assembly of multiple products together are actually serving and solving the system problem and the system's obligations in the case of a variety of conditions that are very difficult to actually demonstrate all the time, such as faults. We'll talk about faults, or highlighted faults, but we can also talk about power quality issues, where it's hard to actually create all kinds of different power quality issues in an electrical system. And we use hardware in the loop solutions in order to try to replicate a variety of variety of situations that occur that we can then show how our products solve for that, and how products assembled solve for that, or how we can fix products that we have or adjust our products to be able to solve for power quality, be able to demonstrate through all the different variations of ways that power systems turn on or off, then how UPSs, uninterruptible power supplies, will work in those conditions, how our microgrid controls that we're working with all of the interactive solutions of inverters, generator controllers, other ancillary DERs, and power management systems to be able to facilitate a behavioral function of all of these assets in all the variety of different kind of power system problems that would be observed. And we can't actually run tests in all of those cases. So having a system that we can show from a model that we can run very quickly, lots and lots of different characteristics of the power system, has enabled us to be able to provide products that you all come to trust and rely to solve your needs.
So next, Scott Manson, Schweitzer Engineering. What problem does the model-based engineering solve?
Well, right quick, introduce myself. I'm Scott Manson, Technology Director. Invented PowerMax. We've got a lot of installed base worldwide, and started back in 2002. To answer your question, I'll get to it in a moment. I recollect 6 weeks in the laboratory trying to model a CT in a hardware loop simulation environment. Even with a master's degree, it took 6 weeks. It was not trivial. After going through that exercise, I realized that the control systems we were designing and inventing and specifically to solve the oil and gas's reliability problems and to prevent blackouts, this was a perfect tool for it. So I immediately jumped on the act of modeling generators, turbines, motors, all of the mechanical assemblies, the steam, all of the things that you don't think immediately as being connected to the electric power system, but they are. At which point, by 2006, I was confident enough to show it to a customer in a real-time factory acceptance test. The customer comes in at the end of our development cycle, before we go to commission, we test it in front of them, and they get the real-life experience of running their control system before they sign off on it and take it home. And this is an incredibly valuable tool for them and us. And this has progressed now today to where we actually bring in black hat hackers, and they'll attack our power system and our control system while we're simultaneously simulating events in the power system, such as generator outages, faults on the utility system, seamless outing events, you name it. Now the value, what does this do? Number one, it grows our employees dramatically faster than we can anywhere else. I mean, when you could put an engineer in front of 1,000 faults in a week, 1,000 short circuit events, and look at the results, he's going to learn a lifetime of career experience in a consolidated period of time. So we can grow our engineers more quickly and grow the kind of solid engineer that we want. The next thing we notice is that during the customer factory acceptance test, where we have tens or dozens of engineers, the most capable engineers in the industry many times come to our facility and ask us the hardest questions they can dream up, try to break our system. Guess what happens? Smart guys make us smarter, make our systems even better. The customer is delighted. When they walk out the door, they're confident in what they pay for, they're confident in us, and that's a return customer. So what does it do? It keeps the cost down, it keeps the quality up, and it achieves our SEL mission, which is making electric power safer, more reliable, more economical.
Okay, thanks, Scott. Our final panelist, Qiang from Eaton Technology.
So I'm a regional technology manager with Eaton, and I'm leading a group, a research group, Denver area. So our team is primarily focusing on the distribution automation and microgrids technology, primarily on the research and development side. How I can provide more perspective of the technology, how the loop can enable new applications. What are the corner cases that you can find out of this test that it'll eventually drive the new technology, commercialized technology into the business. And so throughout all the research type of projects, you can imagine most of the researchers, they cannot even speak without simulation designs, right? So it's part of a critical path to identify the problem, evaluate the algorithm, and eventually be able to transfer new algorithm, new technology into the product. So our group really is right now the essential piece. Out of all the research, all the projects, especially in the microgrid, very unique cases is you have the microgrid with different type of vendors providing different type of technology within that piece of assets. That in order to get more details on the capability of each asset, be able to integrate, be able to achieve the high performance of the entire system, you really need to test it ahead of time and be able to integrate it on site and mitigate all the risks. So, yeah, this is definitely what we see as the most value of the HIL aspect. So, as what all the panelists mentioned, that I would hope that there will be a policy or anything that can drive this out of the loop as part of the standard design approach, that people will see the value. For instance, like 2 years back, you may have already installed a PV with battery that you're able to achieve some microgrid functionalities. But later on, the customer may say, hey, I need to add more EV to my system. What I'm going to do is upgrading it. With the under-the-loop test that potentially deploy or develop, like 2 years back, we were able to just add more asset into the system and test all the corner cases and validate your improvements or validate your solution ahead of time. So it's I see HIL can be a living system that go along with the customer over the times that there are new applications in markets.
Okay, thanks. So we've heard a wide variety of problems then, from being able to get the system to actually work, figuring out what the customer needs, trying that it really does resolve some sort of a need, getting people excited, potentially selling your product. So those are just some of the things that the panelists sort of threw out there. We're interested in your conversation, to help you figure out, how can I use this? Is it really something that's worthwhile? Whatever it is that you want to walk away with. So HG and Matt have microphones, and please take it.
Great. Now we're going to warm up our discussion here. While we get the conversation going on this side of the room, I encourage our panelists to think about a question that you are struggling with as it relates to your experience in this field that you're willing to share with this group. Okay? While you think on that, let's open it up to the audience here and see how we start connecting some dots here. First of all, just show of hands, who are developers in there? Microgrid developers? Let's see the developers. All right, developers here. Let's see the financiers, Microgrid financiers. Who we got there? Okay. I hope you have enough money. Yeah? We don't know how much money you have. Okay, so I did have a question, which earlier we talked about, both for developers and financiers, there was the issue of value of resiliency and how important that is to this entire discussion. To what extent do you feel that hardware in the loop, in terms of model engineering, can have a positive impact on that issue? And I did want to, I don't mind telling you have to go soon. NREL does a tremendous amount of modeling. I thought it would be helpful for you to start off our dialogue with your impressions of this and how it will impact microgrid development.
Sure, thanks. Appreciate the opportunity to chat. And agree with a lot of the panelists, and fortunately our organizations have been able to work together how to solve real world problems ahead of time in the laboratory, reduce risk and reduce costs. Many people might know the National Renewable Energy Laboratory is an asset for the nation. The Department of Energy invested $130 million in an energy system integration facility to do hardware in the loop testing. We worked, for instance, organizations Raytheon and Schneider, or the Miramar Microgrid this summer we toured to do this hardware in the loop testing, to do penetration testing on individual devices. And then there's also a new campus that's called the Flatirons campus, which is at the 20 megawatt scale to do hardware in the loop testing. And again, these are all user facilities. But really, completely agree. I think the panelists have really hit the nail on the head in terms of highlighting the amount of tests that can be done quickly, that can really demonstrate the benefit of the hardware in the loop testing to train engineers, to reduce costs, work with customers. A lot of our customers with the Department of Defense. Another good example of a good partnership is with AES in Kauai, with developing a test bed for large-scale energy storage, controller, and a PV array with a military installation. So for those who are curious about the community microgrid, as an example of before this was deployed, it was tested at Flatirons campus, looking at microgrid controller, actually building a mini replica, all the hardware to test prior to deployment. So again, it's great examples of public-private partnerships, the federal government trying to reduce the risk. Yeah, I completely agree. Look forward to hearing other developers and funders comments on that.
Thank you. Let's give a round of applause going for our panelists. So what kind of questions are coming up on this topic as it relates to the work you do, the projects you're working on, the challenges you're facing? Do you feel that this is something that you want to invest more in, given what you've heard right now?
Kevin Whitener with Portland General Electric. One of the things that concerns us most as we shift from rotating machines to inverter-based technology, particularly islanded, is the lack of fault current contribution by the inverters. And I've heard you give some wonderful examples of what the hardware-in-the-loop modeling can do, and I'm all for it. I'm just wondering, does it dive down to that level? Can I actually look at breaker coordination and with that reduced fault current contribution, making sure I have enough fault current to trip those overcurrent devices?
In my experience is yes. In fact, as we deal with a wide variety of inverters, various manufacturers, with different firmware, with different challenges, with different limitations, and an inverter may have more settings than a relay. There's a tremendous variability in what you're going to get site to site. You have two inverters identically from the factory, look completely different in the field. So as part of the rigorous design process, whereby you control the settings on the inverter, you take that information, put it into a model, you can absolutely replicate the behavior in the field. But I would advise, based on my experience, that you get test data, like actually exercise an inverter in a laboratory with the set known good settings before you model it.
We, in fact, do a lot of work to solve that specific question you're raising. We have laboratories that set up with dedicated hardware systems to begin to model different coordination systems, things that change according to whether you're in idle mode or whether you're grid connected, and whether or not we have a change in settings and parameters of the different breakers that might have to be put in perfection, or the relaying functions and or the configurations of the inverters in order to be able to make a system work. And it's part of the microgrid's control schema to actually be able to reliably go from a grid connected environment where you have one characteristic that's got decades long and more than decades long of understanding of the way the system is going to work from a process of coordination to an inverter-based coordination system, which could be inverter plus a generator plus a variety of solutions. You got to cleanly move between them. It's not one versus the other. There's a transition in between. And having the ability to actually model how the different settings are changing and what the implication of those settings, what those settings have as far as risk related to tripping of devices and or devices shutting offline during that transition is part of what's embedded in the model, in the model-based environment that is used to test the systems.
Yeah, very good answer. Thank you.
Would you help me just do a series of passes to the gentleman there who got the microphone? Pick someone to help you, yeah? You can pick someone in between.
Hi, this is Sayed from Opal Technologies. I have a question for all the panelists over here. For hardware-in-the-loop testing, the main component required is really the real-time simulation that runs in real time. I was wondering if any of you have experience of using real-time simulation and hardware-in-the-loop test in operation of power systems, not only in the design phase, but during operation as well.
So are you talking about prototyping controls in a hardware-in-the-loop simulation environment?
Not necessarily prototyping controls, but what I mean is you're done with the design phase, but when you deploy the microgrid, they have the experience of having the real-time simulator, running a model, and optimizing the operation of the power system while it runs.
Yeah, I certainly do. That is one of our offerings, and I can say that, what I can say is that some of the largest oil and gas facilities in the world are all islands unto themselves. Multiple gigawatts of generation of diverse sources, a complexity of the order of 10 to 15,000 protective relays in a civil job site. And facilities like that find that a real-time simulation running in lockstep with a real power system has tremendous advantages. The way this works, you take the protective relays, which are distributed throughout your power system. They are the eyes and the ears that you can capture the voltages and the currents and all of the data points you need. We call it seeding. What we'll do is we'll take that and we'll seed the model and take a snapshot of the state of the power system and seed the model, keeping the model up to date and accurate at all times. And that's remarkable because that allows operations to go out and test switching scenarios. If they have a dramatic event, say a generator's out of service, they're not sure what's going to happen, they go out there and they can simulate what's going to happen next. And when they do have an oops, maybe they have a problem with setting up a protective relay, or perhaps there's a misbehavior in a governor and a generator, turbine controller, rather, they can go out and simulate that, and they can recreate it. This is excellent for root cause analysis. I could go on. There are a number of countries, China, for example, Korea, South Korea, they both do this full time, and they spend extraordinary amounts of money, and I do believe that it's paying off.
So you're running both a hardware and software digital twin of the environment online. Are you in your sandboxing? You actually sandbox the digital twin for testing purposes?
Yeah, exactly. Yeah.
Thank you.
Just add a few more points here. I mean, from the research point of view, you do want to have a digital replica system running in parallel with your actual system. You're able to identify, as what Scott mentioned, that you're able to do some system identification, keep tuning your model, make the algorithm a little more accurate. It's pretty much, I mean, there are a lot of applications that you can think of. But how do we justify the cost for the microgrid? That's really what we see daily basis. A lot of customers, they don't even have the hardware loop as like a part of their process. How do we enable this? How is the question to some of the customers or the micro developers? How do you see that?
Can you restate your question?
So, how do we look or add another cost on top of deploying the microgrid? How do we justify that? How do we make the microgrid even more economic viable with the hardware-in-the-loop technology along with it? Okay, is anyone?
That's a good question. How do you make it a justifiable component or investment as part of development of a microgrid is having hardware in the loop?
I would challenge that assumption. It's typically a cost reduction, a significant cost reduction to the industry to have to pay for the technology, like an order of magnitude sometimes. Because what happens is because your system goes in quickly, you're not paying your return on investment calculations stay true. You're not worried about a commissioning process that may take weeks or months or years or may never work. There's a great number of microgrids that still aren't on the service today because they were never designed to test it.
So let's go into the audience with that then. This question of what hardware in the loop is it an asset to microgrid development? There's a first cost to it, I'm sure, that you have to justify, even though it has back-end savings and benefits. Are you seeing that as something, as microgrid developers here, you're willing to invest in at the beginning? Sexy Clark, you're saying yes. Any others saying no? It's a showstopper. It's not the time to do that. Thanks for the good. You put that microphone. I haven't dropped it yet. You can do it.
This is pretty funny. I would suggest that or ask if this hardware in the loop would just really become part of that. Oh, I'm sorry. My name is Andy Lynch. I'm from Academy Energy Group. I would ask, everyone's experience here, but also it seemed like it would be logical to take this part and just put it into the pre-commissioning design development phase. Any input on that?
Yeah, so that's a big part of how we do our development now, is we spend a lot of the upfront effort developing concepts of operations to how the system's going to work in order to meet the customer's requirements and how the microgrid is going to operate. A lot of times we are repurposing and dual purposing existing equipment that we can't necessarily change the behavior of or remove and retrofit. So having a real simulation that takes into account all of those different aspects and a lot of the settings for inverters and relays and having, let's say, a physical battery in that simulation allows us to develop and test our operational software against what it sees as the true system. And in doing that, we're able to identify a lot of failure cases which we might have otherwise missed, because, say, you're not going to strip a generator, like a natural generator, offline just to see if your fault detection may damage that piece of equipment. That's something you definitely can do in simulation. So that's my take.
I would say even a step before that, you asked, should you do hardware load simulation as part of the design? We even integrate hardware load simulation before we make sales. It's part of the proposal process. If it's a new application that we're not necessarily confident in how our inversion will respond, we do simulations before even accepting a proposal or bidding on a proposal.
Matt, you have a question on your side?
So we've got a question over here, but one quick question I have for the audience. How many people here know what hardware in the loop is as it relates to model-based engineering and simulation? Is there anybody who's wondering why those terms are being used interchangeably here? Why, perhaps if I could ask the panel, what do you guys mean by hardware in the loop? We're talking model-based engineering, which to me is something on a computer. What's the hardware component that you're putting in the loop that makes this hardware in the loop? Just as a point of clarification, just in case there's anybody else in the audience.
There's one person out there.
Yeah, there's just probably one. That's great. And then,
Well, for us at EPC, the piece of hardware that we connect to the simulator, it's our control board, and it's our control board running actual fielded control software, certified control software. And the hardware, the real-time simulator, in our case, happens to be the Typhoon simulator, simulates our power inverter stage. So everything from the PWM outputs that are generated from the control board, simulates IGBTs, the filter, and then beyond that, out protective devices out to an idealized grid.
and the reason why you put the controller in the loop is for the fidelity piece, correct? And for safety, I mean, you can break your inverter as part of your test regime